Section 1.8 has some applications of linear systems. The first one is polynomial interpolation problem. Let's try to fit a polynomial of degree 2 through 3 given points. Now, a polynomial of degree 2 has 3 unknown coefficients, a0 plus a1t plus a2t squared. So we ought to be able to make it satisfy 3 equations. We plug in the 3 values of t and the 3 values of y, and we get a system of 3 equations and 3 unknowns, which normally, so that's the square system, and normally a square system will have a unique solution. Now if we had 4 points, try to fit a polynomial degree 2 through 4 points, that would be 4 equations and only 3 unknowns, and there would probably be no solution. If we had 3 points and polynomial degree 3, that would have 4 coefficients, then we would have a 3 by 4 system, and that would probably have many solutions. There would be many polynomials degree 3 that pass through those 3 points, because polynomial degree 3 has 4 unknown coefficients. So we want to have the same number of unknowns, the 3 coefficients, as points, equations, so that we have a square system. But that doesn't necessarily guarantee a unique solution. If you have more equations than unknowns, you'll nearly always have no solution. More unknowns than equations, nearly always many solutions. But same number of equations, unknowns, you've got a good chance of a unique solution, but are we guaranteed? Well, in fact, in this problem, we are guaranteed, and there's a nice little proof here. Remember in the previous section that square matrices, they're either non-singular, those are the good matrices, they're the ones that when you reduce them down you get an identity, or they're bad matrices, you reduce them down you get at least one row of zeros. And the good matrices, the non-singular ones, it doesn't matter what the right-hand side is, you'll get a unique solution because you reduce it down to an identity. The bad matrices, the singular ones, it doesn't matter what the right-hand side is, when you reduce it down you get a row of zeros, and you'll either get many solutions or no solutions depending on whether the b's corresponding to those rows of 0 or 0. So you're either going to always get a unique solution or you're never going to get a unique solution. Well, this is one of the non-singular problems where you're always going to get a unique solution. And to prove that, just suppose your y's happen to be 0, then your system of equations is this. And we know that has a unique solution. Why? Because we have a polynomial degree 2 with 3 distinct roots. We're assuming t0, t1, and t2 are different from each other. Then we have 3 distinct roots, and a polynomial degree 2 can't have more than 2 roots except for the polynomial of all zeros. So the C0, C1, C2 must be all zeros. That's the only way you could have 3 roots. Of course, if you have all zeros, you've got an infinite number of roots, but anything else, you'll have at most 2 roots. So that proves that if the right-hand side were 0, you get a unique solution, which proves that your matrix is non-singular. It's a good matrix, so whatever the right-hand side is, you're going to have a unique solution. In general, if you have a polynomial degree n, which has n plus 1 coefficients, you can fit it through uniquely through n plus 1 points. If you try to fit it through more points than that, it's probably no solution. Fewer points, many solutions, usually. Okay, now I'm going to solve 3 problems that are very similar to your homework problems in this section. The first one is actually problem 6, fit a polynomial of degree 3 through 4 points. Well, polynomial degree 3 has 4 unknown coefficients, a0, a1, a2, and a3. So we ought to be able to fit it through 4 points. Just plug in t equals minus 2, and that's a0 plus a1 times minus 2 plus a2 times t squared plus a3 times t cubed is equal to minus 3. It's the first equation, forcing it to pass through the first point. Second equation forces it to pass through the second point, and so forth. So you got 4 points, 4 unknown coefficients for a polynomial degree 3. Have a square linear system, and we're going to solve that using MATLAB in a moment. Well, let's go ahead and do it now. So here's the problem 6. There's the matrix A6 and the right-hand side, and we'll solve it using MATLAB. You just say A6 backslash B6. That's basically saying solve A6 X6 equals B6. So solve the system with A6 is the matrix, B6 is the right-hand side. And so let's run it. I've actually run all 3 problems there. Let's go back up. Here's the problem we're looking at. There's the matrix. There's the 4 t points. There's the 4 y points, t squared, t cubed. And there's the solution, 1, 0, 1, 1, which means 1 plus 0t plus 1t squared plus 1t cubed. So using MATLAB, that's the solution. And you can easily verify. You plug in t equals -2 and you get -3. Plug in t equals -1, you get 1, and so forth. So it does pass through the 4 points. The next problem is also very similar to one of your homework problems. It's approximating the integral of a function. And we want to approximate the integral from 0 to h of f of t as a linear combination of f at the left-hand point 1/4 of the way through, 1/2, 3/4, and 1. So you're evaluating f at the left-hand point, the right-hand point, and 3 points in between uniformly spaced. What are the best weights to give you the highest accuracy? Well, we actually show in numerical analysis 4329 that the order of accuracy for general functions f of a quadrature method depends on the degree of precision. That is, the higher the degree polynomial that it's exact for, the more accurate it is for general functions that aren't polynomials. So we want to make this exact for as high degree polynomials as possible. Well, we've got 5 unknown coefficients, so we ought to be able to make it exact for 1, t, t squared, t cubed, and t fourth, and therefore any polynomial of degree 4. Because that will be 5 equations and 5 unknowns. We always want nearly always want the same number of equations as unknowns. So we try to make this exact for 1, t, t squared, and so forth. So you plug in f of t equals to 1, and f of anything is 1, so that's just 1 times a0 plus 1 times a1 plus 1 times a2 plus 1 times a3 plus 1 times a4 equals the integral of 1, which is the antiderivative of 1 is t. Plug in the upper limit, you get h minus 0, so you get h. Now do the same thing with t. Plug in f of t equals t. That means f of 0 is 0. F of 0.25h is 0.25h. F of 0.5h is 0.5h, and so forth. And that has to come out to be the integral of t, which is 1/2 t squared. Plug in the upper limits, 1/2 h squared. And keep going, plug in t squared. This is the left-hand point squared, the first point squared, second point squared, third point, last point squared, and the integral of t squared is h cubed over 3, and so forth. So we got 5 equations and 5 unknowns. If we can solve that, we should have weights, coefficients a, which make this exact for polynomials degree 4, and from numerical analysis we know that makes it order h to the 5th accuracy. Well, we want to get rid of this h here, so we divide the second equation through by h, third equation by h squared, and so forth, and get rid of all the h's here. And there's 1 h left in each of these, but I'm just going to take it out, so we don't want to have h in any of the matrix or the right-hand side. We'll solve this system, then we'll just multiply it by h. And so let's solve that using MATLAB. Well, that's I'm actually solving all 3 problems in the same program here. Here, the second one, there's the first row of the A, second row, 0 squared, 1/4 h squared, 1/2 h squared, 3/4 h squared, h squared, and so forth. Right-hand side, those were the integrals of h of 1, t, t squared, t cubed, t to the 4th power, and we solved the system. And I've actually already done that. Here's the matrix printed out. And the right-hand side, 1, 1/2, 1/3, 1/4, 1/5. And there's the solution. Those are the coefficients, the weights. And that's where these came from, converted to fractions. This was 7/90ths, A0 was 7/90ths, A1 was 32/90ths, and so forth. And then I put the H in there because I ignored that when I solved the problem. Okay, now the third problem is very similar to one of your homework problems also. It's problem 20. And this is approximating a derivative. So you can use these examples to approximate integrals and now derivatives. This is problems, all three of these are problems we do in 4329. So we say we want to approximate f prime at 0 by a linear combination of the values of f at 0, h, 2h, and 3h. And again, you can show that the higher degree polynomial of this formula is exact for, the more accurate it is for general functions. So we want to make it exact for what? Well, we've got 4 unknown coefficients, so we ought to be able to make it exact for 1, t squared, and t cubed, and therefore all polynomials of degree 3 or less. So we always gun for same number of equations as unknowns because we've got a good chance of a unique solution. And so you plug in f of t equals 1, and you get a0 times 1 plus a1 times 1 plus a2 times 1 plus a3 times 1 equals, the derivative of 1 is 0 at any point, so that's where the 0 comes from. Then plug in t, and f of 0 is 0, f of h is h, f of 2h is 2h, f of 3h is 3h. That has to be the derivative of t, which is 1 at any point, so there's the 1. And then plug in t squared. F of 0 is 0 squared, f of h is h squared, f of 2h is 2h squared, f of 3h is 3h squared. That has to be the derivative of t squared at 0. Well, derivative of t squared is 2t. You plug in t equals 0, that's 0, and the t cubed is also 0. The derivative is 3t squared. So both at t equals 0, they're both 0. So there's our system of 4 equations, 4 unknowns. I don't like the h's in there, so I divide the first equation through by h, second equation by h squared, third equation by h cubed, and these are all 0 except you have a 1 over h there, but I'm going to take the 1 over h out and solve this system, and then I'll add the 1 over h in the solution. So again, we use MATLAB to solve this system. And that was the third problem in my MATLAB program here. The first row, remember, is all 1s, and that was 0, 1, 2, 3, 0, 1 squared, 2 squared, 3 squared, 0, 1 cubed, 2 cubed, 3 cubed. Right inside was 0, 1, 0, 0. Actually, that was 1 over h, but I'm saving the 1 over h. Then I solved the system, and we've already done that also. The solution was here. And when I convert that to fractions and put back the 1 over h, I get this. That is an approximation to the derivative of f at 0. Obviously, if you want to approximate the derivative of f at some other point, then let's say f prime at c, then this would just be c plus h, c plus 2h, c plus 3h. So this is more useful than it looks like. Same thing with the approximation of the integrals. If you're not integrating from 0 to h, you're integrating from a to b, then this would just be a, and that would be b, and that would be midpoint and 1/4 and 3/4 point, so forth. So your homework problems are very similar to these three in section 1.8.